Okay, in part 3 of chapter 25, we're looking at transformers and power transmission. So we were just talking about how Tesla won the war on currents. And one of the main reasons is because of transformers, which are not robots in disguise, by the way. Transformers are an electrical device that allows you to put in one voltage and get out a different voltage. And so they're amazing things. I know that doesn't sound very impressive, but it is. And the thing is that you can't use them with DC. They only work with alternating current. Okay, so let's talk about transformers. Well, for one thing, they're all around you all the time. There's a primary coil and a secondary coil, and usually they're hidden. So you know those boxes that are all over your house charging things? Okay, so we've talked about how there's a rectifier in these to transform alternating current from your wall into DC to go into your battery. But there's also a transformer in there. Because we have to transform the 120 volts of electricity from the wall into the 6 or 9 volts that you need for your device. So what happens is that you have to transform it into a lower voltage. Okay, so that's chargers all around you. And what they do is they either step up or step down voltage. So step up means they increase the voltage. Step down, decrease the voltage. Okay, so voltage up, voltage down. And the transformer has those 2 coils. They're wrapped around, again, an iron core. That helps concentrate the magnetic field, as usual, by lining up the domains. And the magnetic field is produced in a primary coil. So how does that happen? You're putting alternating current into a coil of wire. That creates a magnetic field, right? And that magnetic field will go through the secondary coil. Okay, so we're going to look at this in a moment with illustrations. And what we end up with is a voltage and a current out of the second coil. So even though they're not attached to each other, okay, so the coils don't touch, what happens though is we get current output and voltage output. So let's see how that works. So just think about this. You're putting in alternating current. Okay, so what that's going to do is that's going to create some magnetic fields, right? You're putting it into a coil of wire. Now, since it's alternating current, well, you produce a magnetic field. That is going to run through this whole soft iron, right? Lining up the domains. And you end up with, it's like you thrust a magnet into the secondary coil, right? So you just started with electricity in the primary coil, but now you've ended up with a magnetic field in the secondary coil. After a while, of course, since it's AC, what's going to happen is the current reverses. That reverses the direction of the induced magnetic field. And that is now circling, okay? And so you end up with now what looks like a magnet being thrust the opposite direction of the secondary coil. So the magnet looks like it looks like a magnet that would thrust into one side and then was pulled back out. And so as the primary coil keeps experiencing this alternating current, then it's like a magnet just keeps getting thrust in and out of the secondary coil. Okay, so let's go look at this some more. All right, so here's showing the idea of having more coils. Okay, so you're going to get a current in and you get a current out, or a voltage in gives you a voltage out. as long as you've got AC current. So with one loop here and one loop here, then the 1 volt you put in, you get out 1 volt. But what if you had 2 loops? Well, then it's like you were thrusting the magnet in 2 loops. So you get out 2 volts, 1 and 1. Well, what if that was just 2 continuous loops? Well, you would still get 2 volts out. So it's really cool. You're putting in 1 volt, but you're getting out 2 volts. Okay, so 1 volt AC in, 2 volts AC out. What if I add a 3rd loop, right? Well, 3rd loop means I'm going to get 3 volts, right? Each loop is producing a certain amount of voltage. Okay, so one of the ways to think about this is the primary voltage gets spread over the number of loops. So here we've got 5 loops, and let's say that we are putting in 10 volts. Okay, so I'm putting 10 volts AC in. Okay, I've got 5 loops, and basically it's like that 10 volts gets spread over those 5 loops. So I would have 2 volts in each loop. It's kind of like the batteries that are getting stacked up. Okay, so I would end up with 2 times 5. That's 10 volts. Now, the cool thing is on the other side, each loop is also worth 2 volts. But I have 15 loops on the other side. So on this side, in 1, the number of loops was 5. On the secondary side, in 2, the number of loops is 15. But each one of these is now worth 2. So how many volts would I end up with? 2 times 15, or 30 volts out. Okay, so primary voltage over number of turns, so in this case 10 over 5, is going to equal the secondary voltage over the number of secondary turns, equals 30 over 15, right? 2 equals 2. Okay, so that's the idea, is you can do this by ratios. V1 over N1 equals V2 over N2. Okay, so let's look at this same transformer, but now we're going to look at it when we put in 20 volts AC. All right, and what we're going to do is we want to find out the secondary voltage. So we can rewrite this formula for V2. So let's rewrite it. V2 is going to equal V1 times N2 over N1. So it's the ratio of the windings, the coils there, that is the key to understanding this particular transformer. Because this transformer has a ratio of N2 over N1. That's 15, right, is N2, and 5 is N1. So my ratio is 15 over 5, which is 3, right? So whatever voltage I put in, I'm going to put in 20 volts this time, it's always going to get multiplied by that ratio. So V2, the secondary voltage, is 60. So I put in 20. Nope. Pen is not working well. I put in 20, and I got out 60. When I put in 10, I got out 30, right? It's always, this transformer is always going to give 3 times as much voltage. And that makes it, of course, a step up transformer, right? More windings gives you more voltage. Okay, so when your in goes up, that makes this a step up. More voltage on the secondary side. Okay, so anyway, so that's how transformers work. Now, why is that important? Because that means that you can easily transform voltage to much, much higher voltages. And then you can have high voltage transmission lines, which are very important. So we'll be talking about that. Okay, now here's kind of a homework problem, trick question. Well, it doesn't look like a trick. You've got 10 turns on this side, right? That's in 1. You've got 100 turns there. So what your brain should be saying is, okay, the ratio is N2 over N1. This is N1. This is N2. And that's 100 over 10. So this is going to be a step-up transformer, and it'll multiply things by 10, right? Okay, so your brain, it probably is going there. But look over here. It's a trick because it says DC. DC is not going to work. So we can only work if we put in AC. So, okay, so let's say this is AC. You put in 12 volts AC on the primary side. So that's V1. What's V2? Well, you're going to get 12 times 10. So it's going to be 120, right? Because your ratio is always going to be 10 with this transformer. Okay, so DC doesn't work because you're not, it's like you thrust a magnet into the secondary coil once, but then it just stuck there. And in that case, you're not going to get any current being produced. Okay, you got to have a changing magnetic field. And the DC, you just get one thrust of a magnet and then nothing till it turns off. Okay, so primary has an input, but again, not a battery. It's got to be alternating current. Okay, so watch out for that. All right, so like I said, transformers are everywhere. There's step-up ones, there's step-down ones. They are, usually you convert 120 volts using these household ones down to however much your phone or your computer needs. And remember, there's a diode inside to make sure you get DC for the battery. But you also, if you see these on power poles, those trash basket looking things are transformers also. And they're taking the high voltage lines, which are coming in at like 2400 volts, and reducing them to 240 volts to go down to your house. So it actually cuts it down by 1/10, right? Now, Tesla wanted everybody to use wireless power transfer, and we finally are. So he was like 100 years or more ahead of his time. And so if you've got a wireless charger, basically what you've got is a coil of wire in here that is producing a magnetic field. Then you've got a coil of wire in your phone or in the attachment that is picking up that changing magnetic field and turning it into electricity to charge your battery. Okay, so here's that equation. V2 is N2 over N1 times the voltage one. Now, when you look on the equation sheet, there is a special little section for transformers. But I wrote them to be the easiest way to write them out. So the voltage one looks like this. It looks something like V2 N1 equals V1 N2, because that would be the same thing. And that's easier for me to write out. Okay, so it still works, but it just doesn't have much meaning left. So you might want to write some other ones. So you're going to have several of these, of course, on the next test. So here we've got a transformer that has 500 winding in its primary, but only 25 in its secondary. So is this a step up or a step down? It's going to be a step down. Voltage goes with the windings. The windings go from 500 to 25. So that's a drop of 1/200th or 1/20th. Let's see. So that means that it's going to drop down, okay, to a lower voltage. So the primary voltage is 4,400. So we can use the equation. All right, put in all the numbers. So we have V1 is 4,400. The ratio N2 over N1 is 25 over 500. And that's 1/20th, so it cuts down the voltage to 220 volts. So it's a step down. And so this is pretty typical on utility poles. Okay, now energy must be conserved. So one of the things is we've got magically more voltage or less voltage. But what about energy? Well, energy relates to power. Power is energy per time, so per second. So the idea is that if we want energy to be conserved, we have to have power conserved, the energy used per second. So the power input of the primary equals the power output of the secondary. So V1 I1 equals V2 I2. Okay, so what that means is that if our voltage goes up, because it's a step-up transformer, then our current is going to have to go down, okay, to keep everything balanced. And the same thing if it's a step-down transformer where voltage goes down, then the current is going to have to go up to keep it equal to the original amount. Okay, so there's always a trade-off. In this case, if you get more voltage, you get less current. Okay, so back to that problem we did a few minutes ago. This transformer has 5 turns in the primary, 15 in the secondary. The primary voltage was 20 volts AC. What's the voltage in the secondary coil? So we answered that. So our primary voltage was 20 volts. And remember the ratio was 3 between 15 and 5, right? And remember our output then, V2, was 60 volts. Okay, because it was 3 times greater. So we got our voltage. Now let's say the primary current is 9 amps. The question is, what is the secondary current? All right, so we can use this formula. V1 I1 equals V2 I2. We've got everything except I2. So we've got V1 was 20 volts. I1 is 9 amps. On the other side, we're going to have V2, which is 60 volts, and I2, which is what we want to find out. Okay, so we just need to move it around. So I2 is going to be 20 volts over 60 volts times 9 amps, which is going to be 1/3 of 9, which comes out to 3 amps. So I2 is 3 amps. And again, that's because our voltage went up by 3. It was magnified by 3. So our current had to be reduced to 1/3 of its value. So it went from 9 to 3. Now, there is a formula that just involves current and the in numbers. Let's see if I have it here. Oh, nope, I don't seem to have it there. Okay, so let's give you the current one, which is in1 equals I1. Oops, sorry, just screwed that up. Forget that that happened. Okay, let's try that again. I2, I1. Oh, shoot. Keep doing this. All right, sorry, it's late at night here. Stop it. Okay, let's try this again. I2 in1, no, in2 equals I1 in1. Okay, my brain is refusing to do it. It doesn't like that equation. Anyway, so that would give you the same thing, or you can write it out as I2 equals N1 over N2 times I1. That's the way I usually use it. So that's one reason my brain wouldn't go the other way. But that's the way these are written on your equation sheet. Easy to write out, but the meaning kind of gets lost. All right, so we're going to write them down as this one and this one, so you can always find the voltage or the current. And the main difference between these is that the ratio got turned upside down. Here it's N2 over N1 for voltage, and here it's N1 over N2 for current. Okay, and so again, why is that important? Well, because you want really high voltages, which reduces the current. The less current you have, the less heat loss. And so that's why we have high voltage lines that crisscross the country, because then they can carry the power for many miles without losing a lot of energy. Remember, we talked about how Edison needed the power plants every couple of miles because his current was full strength. So there was a lot of losses of energy. But if we can have really, really, really high voltages, then our current reduces to almost nothing, which is strange. Okay, so you get voltage, but not current. And then as you get closer to homes, so you take it from the power plant, step it up to unbelievably high voltages, which are what's in those transmission lines, but now there's hardly any current. So the molecules, the electrons are hardly moving at all, just gently, a tiny little bit wiggling around in the power lines. And then as you get closer to a city, you would start to transform it down to 2400. That would run along the lines through the streets, get close to the house, and they would break down to 240. And then that gets split basically to 120. And that's what most of your house is wired in, 120, with occasionally 240s for the for like the washer and stuff like that. Anyway, so this means that during the long distance part, voltage went up. So current, oops, that's supposed to be voltage. Voltage went up, current went down, and therefore you had very little heat loss. So that's how we can have a power plant way over on the Rock River that's providing us with power. It's not down the next block. So most of us don't even have any idea where our power plants are. Okay, so anyway, so transmission lines, that's where Tesla really won the war on currents, because he could use transformers. But like I said, transformers can blow up occasionally when there's fires and floods and electrical storms from space. So unfortunately, sometimes these things go out of action. Like we have some on some poles near us. They had issues this summer, and so we lost electricity for a while, and they had to replace our transformers because they were no longer working. Now, there are often these very, very large transformers too at area substations. And it says restricted area, danger, high voltage, keep out. They mean it. Okay, high voltage is nothing to play around with. And so anyway, so all over the world, Teslas, alternating current generators and motors and transformers are being used. Okay, and that's the end of part 3. We've just got like a tiny little bit for part 4. So we will start and stop and talk about field induction and Tesla coils next.